Well, hello everyone. Thank you for joining today's session. Once again, my name is Agilo Christian. I'm reaching you from Port Harcourt, Nigeria. I'm the Assistant Programs Coordinator at HAMOE. Thank you again for joining us in this live coding session brought to you by HAMOE. And this will be our 6th session for this 4 cohorts. Okay, topic we'll be dealing on today will be machine learning classification problem. Yeah, so we already dealt with machine learning regression problems, so today we'll be dealing with machine learning classification. So I see we already have a few participants already on YouTube and also on Zoom. You're very welcome. So we'll have a lot to do today, so I'll just get on to what we're doing immediately. So I'll share my screen now. And also for today, I'll be the host for today and the anchor. I'll handle today's session. All right, let's start. Let me share my screen. I'm guessing you can see my screen. If you can just drop it in the chat so I move on. Okay, good. All right, so like I said, we'll be doing a classification problem, but the problem we're dealing with would be we're going to predict a heart disease using machine learning. So normally this notebook contains the classification of heart disease if a patient has a heart disease or not. And as usual, due to time, I've already wrote down the code, and I'll just explain as I move on. All right. The problem definition, it involves binary classification. That's a sample can only be one of two things, yes or no, if the person has heart disease or not. So which involves using a number of different features about a person to predict whether they have heart disease or not. So the data was gotten from the Cleveland database from UCI Machine Learning Repository. So, and the features of the data set, it has 14 features. You have the age, the sex, the CP, the code, stress, the FBS, which is the blood sugar. So these are just the features of the data set. So moving on to the code. So I'll be importing the necessary libraries needs, and also our estimators will be using. I'm working with logistic regression, k-numbers classifier, and random forest classifier. Then I'll be importing the train test splits, crossbar, score, and all that. Okay, what I'll be doing basically will be analysis, the modeling, model evaluation, tuning the hyperparameters. That is after we've gotten our model to see if it will improve or not. So let's just get started. Okay, download the data. Okay, these are data, like I said, that's 14 features, that's 14 columns. They'll have a target column. We're predicting if a patient has heart disease or not. So 1 represents yes, 0 represents no. So this will be our target. Being on data sets, the last part of data sets. Then shape. And getting the value count of our targets. Okay, we see from our data sets, 165 is 1, then 138 is 0. So it's not that balanced, but it's quite okay. So this is the target column for 1 represents yes, 0 represents no of our data set. So we've not started running our modeling or not. So I'm going to plot it so you understand. This is just some analysis and doing visualization to understand our data better. All right, getting the info. After that, seeing if there's a missing data or not. Then another analysis for describe. Well, I'm just running through this because we already know on this part, so it's just some wrangling I'm doing on data to see what's up. So now I'll be doing some few analysis to understand my data sets better. So you remember in the column, we have a sex column. So I want to see how many male or female we have in our data sets. So based on our round score before, so I knew that we have 207 males and 96 females. So I'll do a cross tab to get to understand it better. So in our data sets, the number of male or female, 24 of the female does not have heart disease, then 72 has. So this is just like to understand data set better, to see with the sex and targets from the data set first before doing our analysis or running our model. Okay, then I just want to represent this visually. I need to see. So the frequency of the heart disease from our data, 0 means no disease. So it means from our data set, the sex, that is female, they don't have a heart disease. That we have less than it was the male that has more heart disease from the data set provided. So this is before carrying out modeling. So just to view some part of the data lash. Then also do another visualization of checking the age versus the mass heart rate. So these are things you can do to carry out your data to understand your data set better. So what this code is doing here, I want to plot a scatter diagram to make me understand my data sets better. So it is not like a preamble or a necessary thing you should do. You should just your personal stuff if you want to understand your data set better. So this is just what I'm doing to get a visual of my data set before I run the model. So this will show me the age versus the mass heart rate for the disease. These are the features in the data set provided. So the scatter plot is showing the red means no disease, then this other golden rod color means no disease. So meaning as the age increases, there's chances that the patient has heart disease. So it's just what this is representing. So I'm just plotting this plot. I hope everyone can hear me clearly. Just signify by dropping it in the chat. So I continue. Okay. All right, doing another analysis, heart disease frequency per chest pain. So I just basically preamble, just run through it before we get to the modeling proper. You can go back to this video to understand this codes and what I've been doing. These are just visualization codes to make me understand my data set better. So the frequency, heart disease frequency per chest pain type. In chest pain type, in our data set, we have 4 different chest pain types, 0 to 3. It's already represented in the data sets. So let me just scroll up so you understand what that was about. Chest pain type. So 0 means typical angina, 1 atypical angina, 3 non-angina pain, and 3 asymptomatic, means chest pain not showing signs of disease. So these are just the features in the data set. So I'm not go deep into it. So I'm just running the analysis to see. Because normally when you're running your model, you need to understand your data set better. So you know how you run your model. So checking out, loading our data set again, doing a correlation metrics to find the correlation between the independent and dependent, between the independent variables. So I just want to put this in a visual so you understand better. Okay. So these are features that are correlated. Trace BP is more correlated here to the CP, which is heart rate type. So this is just basic analysis and visualizations. I'm not going to explain more. So now getting to the business of the day, which is the modeling part. As usual, we already know this part. We have to split our data sets into X and Y. The X will be the targets. That's why we're dropping the targets. The X will be the data set except targets column, and the Y will be just the targets column. Times like I'm not going to run this X or Y. So we're splitting the data sets into train and test sets. Using a random seed at 42 and test size at 20%. So it's mean train size 80, test size 20. That's train, Y train. Then putting it, like I said before we started, I'll be using 3 different estimators, the logistic regression. This is just my choice. And mind you, there are classification estimators. We also have estimators for regression problem. How you know a classification problem is, like I said from the beginning, you're classifying something is this or that. So if like a problem statement, we want to classify if a patient has had disease or not. So that's the classification problem. So we'll be using the logistic regression, as also use k-neighbors classifier and random forest classifier. So creating a function to get the scores of the 3 at once instead of running the codes individually. So this is what this function is just doing. It will fit it and to score it to return the scores of the 3 estimators. So it's done. And I get the model scores of the 3 estimators. So from our score, if you can see my screen, logistic regression performed better. So let's just compare them to see in a more visual way. So if you see from this visualization, logistic regression is perform better than KNN or random forest. So now, since logistic regression and random forest classifier, and mind you, logistic regression, because of the regression, you hear the name regression, you can also use it for a regression problem and a classification problem. But it is not linear regression. Linear regression is for just regression problem. But logistic regression, you can use for a regression problem and a classification problem. So in case you want to ask that question. So since these 2 models performed well, we're going to tune both models to see if it will improve better, because we have a score. And mind you, in classification problem, the default score is the accuracy. In regression, the default score is the R squared, that's the R2 score. So for this, it got an accuracy of 0.8. The random forest had an accuracy of 0.83. So we're going to tune them to see which will perform better. So before we go there, let me just explain what the 2 hyperparameter tuning functions we can use. So we have the random search CV and the grid search CV. So random search CV is a method in which random combinations of hyperparameters are selected and used to train a model. The best random hyperparameter combinations are used. So it means the method of using the random combinations of the parameters, you select a particular parameter in that estimator to see if you can fine-tune it, if it will improve the model or not. The Y-grid search CV is a technique to search through the best parameter values from the given set of the grid of parameters. So it's basically a cross-validation method, and the model and the parameters are required to be fed in. The best parameter values are extracted and then the predictions are made. So the difference between both is that the approaches in grid search CV we define the combinations and do training of the model. Whereas in random search CV, the model selects the combination randomly. But in grid search CV, you are the one to do the combinations and do training of the model. So random search CV selects the combination randomly. So both are very effective ways of tuning the parameters that will increase the model generalizability. So enough talk, let's get down to the code. So we're tuning logistic regression model and the random forest classifier model. All right. So the way we tune the logistic regression, if you notice once you load your logistic regression, there are several parameters in it. Let me just see if this will load. There are several parameters in it. So what I'll be tuning the log space, then also the solver, which is the lib linear. So these are the two parameters I want to tune in this logistic regression estimator. So I just want to create the hyperparameter grid for logistic regression. Then for the random forest classifier, I'll be tuning the number of estimators, the mass steps, the minimum sample splits, and the minimum samples lead. If you don't understand, if you go to the documentation of these two estimators, they have parameters in it, inbuilt parameters. So you can tune whichever one you think you can tune that will improve the model or not. So this is the parameter that's selected for both models. So moving on, then let me tune the logistic regression. To tune that, I'm using random search CV first of all. So by doing that, you put in the model you want to tune, then the parameter distribution. So this is part of the documentation in random search CV. Okay, if you can see it now on my screen, the random search CV has different parameters on which you impute in code. You have the estimator, the param distributions, the number of iterations, the scoring, and jobs and all that. So that's what I'll be feeding into the random search CV. So I'm putting in my estimator, which is the logistic regression, then the distributions that I want to tune, which I said was the solver and the log space. And I'm using the CV of 5, that's cross validation of 5. Then number of iterations will be 20, they're both true. So let me just tune that, wait for it to load. Wow, that was fast. So after doing that, we search for the best parameters. So the best parameters was the solver was lib linear and C was this amount. So let's score it to see if it will improve or not. So the difference wasn't that much. It scored 0.88. Previously, the previous score, if you go back to the code, was 0.88. So it didn't really improve, basically, after tuning the parameters. So we also tune the parameters for the random forest classifier using the same method we used before for the random search CV. Let's see if it will improve or not. Wait for that to load. In case you don't understand, you can drop your questions in the chat when I'm done. I'll review it. So for this, I'm using 30 number of iterations, but I'm using a cross validation of 5. So you see, it is fitting 5 folds for each of 30 candidates. So the total fit to be 150. So just wait for it to load. It will take time. And mind you, I'm doing this on Colab. So if you are doing it on your personal computer, probably using the Jupyter notebook, it takes space and time. So Colab was faster. So if I was running on my personal computer, if you don't have a lot of RAM PC, it might slow down. So even with Colab now, and I'm on normal CPU, not a CPU or GPU processor. So it might take like 2 minutes to tune because I'm tuning for 150 fits. So number of iterations 30 to cross validate it for 5 different cross validations. So 30 times is 55 or 50 fits. So I just wait for it to load. Okay. And it takes a lot of time to tune the hyperparameters. So, okay, well done. Just tuned it and I fixed it to the H train and the Y train. So let's see the best parameters. So the best parameters was the estimator to be 260, minimum sample speed 16, sample speed 17, mass depth was 3. So let's score it to see if it will improve or not. So it's actually improved from the previous score. The previous score was 0.83. Now I got 0.86, but still the logistic regression had a better performance, a better accuracy. So we'll just go with that. So since logistic regression performed better, we're still going to tune the logistic regression model using grid search CV before we use random search CV. So we're going to pass in the grid. So I'm tuning the C and the solver. If you check the logistic regression documentation, you see the different parameters in it to have the C and the solver. So you can do your research to know which one you would like to tune or not. So me personally, I'm tuning the C and the solver. Then passing it to the grid search CV function using 5 cross validation, then fitting into the H train and the Y train. Okay, that was fast. Then let's see the best parameters we got. Solver was linear, C was 0.204. So let's score it to see if it improved or not. It actually didn't also improve further. So the best score after tuning this logistic regression was also 0.88. So mind you, you can also tune other parameters in logistic regression. So that's what you can decide to do after this video, to check for that to see how you can handle it, if it will improve or not. So, but here, this is the only 2 parameters I'll be tuning. So now we're going to evaluate the tuned machine learning classifier beyond accuracy. Beyond accuracy means we can evaluate the in classification. There are different ways of evaluating it. Like in regression, we have the mean absolute error, the mean squared error, blah blah blah. But in classification problem, there's something called the confusion matrix. We have the F1 score, the precision, the accuracy, and all that. So let me just start with the code. You understand what I'm talking about. So making predictions, first of all, we're predicting using this our logistic regression model. So let's view the Y prints. These are the predictions it has made. Let's see our Y test. So let's get the confusion matrix. So in confusion matrix, we have what we call the true positive, the true negative, the false positive, and the false negative. What that means is that, okay, before I go there, let me just put this more in a visual so you understand better. Let me put this result we got in a good visual so you understand better. Okay, so what it means basically, in confusion matrix, it will tell you the 4 different labels: true positive, true negative, false positive, false negative. True negative is when the actual value is 1, the model predicts 1. True negative is when the actual value is 0, the model predicts 0. False positive is when the actual value is 0 and the model predicts 1. The false negative is when the actual value is 1 and the model predicted 0. So for example, now in this heart disease stuff, if a person really has heart disease from everything and the model is predicting does not have, so that is a false negative. Then if person actually has a heart disease, then your model tells you it has a heart disease. So that is true positive. So you can go back to understand it better. So for our model, it's saying It's predicting 25 to be the true negative, meaning they don't actually have heart disease. This is the predicted label, this is the true label. But it's saying 4 has 4 does not have heart disease, whereas they actually have heart disease. This is what this confusion matrix is explaining. So you can go back and understand it better. So there's another thing called the classification reports, which contains the F1 score, the recall, and the precision, and also the accuracy. So this is just the classification reports. I won't be doing more of this. You can go back and understand better. So let me just explain what's there's another way of analyzing your model. So it's called the cross-validation score, other than the normal one. Cross-validation score, let me just explain it. Cross-validation is a function in the scikit-learn package, which trains and tests a model over multiple data sets. This cross-validation method gives you a better understanding of the model performance over the whole data set, instead of just a single train test split. The one we did before was just a single train test split, but this cross-validation gives you a better understanding of your model performance over the whole data set, as it will cross-validate it in different sizes, depending on the amount you put in, probably 5 CV or 10 CV or whatever. So it's also used as a simple cross-validation technique to prevent overfitting and promote model generalization. So you should know what overfitting is. Go back and understand. So loading our best params again, calling our model. So running the cross-val score. In a cross-validation score, if you go to the documentation, you pass in your estimator, your X, your Y, and the scoring method. So the scoring method, I want to check nice for the accuracy. Got that to be 0.84 using the cross-validation method. But with the normal train test splits, we had 0.88. So check it for the precision with cross-validation. 0.82, checking for the recall score. To know what is accuracy, precision, and recall score, you can go back and also F1 score, go back and do your research to see if you understand it better. I'm not be doing more of that. And let's just visualize it, the matrix. So our model, these are the metrics we got. We got our accuracy of 0.8, the precision of this, the recall of this, and an F1 score of this. So depending on the problem you're trying to solve, it's not necessarily use accuracy. For some particular classification problem, you might have a high accuracy, but that's not the right matrix to use. So meaning that sometimes you can have a high accuracy, but the model is overfitting, or it is generally good, not overfitting. So there are some problems you have. The best metric to consider might be precision or recall. Like for this example, precision will be good based on your classifying if person have heart disease or not. So just if you go back and read more on what these metrics score for classification reports are, you understand better what I'm trying to say. So doing our feature importance, calling our model again, fitting in an S train and Y train, checking the coefficients, that's the important part. So let me just put this in the dictionary. So this represents the different columns, the features in our model. So this was the age, sex, the CP, and all that. So let me put it in the visual so you understand better. Okay, I'll go back to your question. So for these are the feature importance, how the model, that's the different features in the model, how are they important to the model general, basically. So if you notice, the CP has a higher one, some are even negative, so meaning it is not, doesn't necessarily affect how the model is predicting, making the predictions. So let me explain it here. So some are negative, some are positive. The larger the value, the more the feature contributes to the model. So in this, the CP, which is the chest pain type, contributes more to the model. If the value is negative, it means there is a negative correlation, and vice versa for positive values. For example, the sex attributes, which is this, has a negative value of 0 minus 0.94, which means as the value for sets increases, the target value decreases. So it means as the value for the sets increases, for example, if for our model 0 means female, 1 means male. So from the model we got, if you notice in the visualization I did before, the male gender has more heart disease than the female. So that's what this model just learned from the data fed into it. So as the sets increase from 0 to 1, that's from female to male, the target values decreases. So that's just it means. So this become more clear by comparing the sex column to target column. Let's just do a cross tab with that, like we did before. If you notice, in the sex, 0 means female, 1 means male. 24 female doesn't have heart disease from data sets. 72 has. Then the male, 114 male does not have heart disease, then 93 has. But still with this, more male had heart disease than the female. So you can see when sex is 0 female, there are almost 3 times as many people with heart disease than without. So, and then as sex increases to male, the ratio goes down to almost like 1 versus 1 of people who have heart disease and who don't. So this means the model has found a pattern which reflects the data. Because from the data, what you got from the data, like I said, there were more male that had heart disease generally, because we see it's 93, and that does not have also 114. So the model has already found pattern from data. And looking at these figures and this specific data set, it means if the patient is female, they are more likely to have heart disease based on the data is not balanced. If you notice, it is imbalanced. There were more male than female, but still 72 of them had heart disease. Let me not confuse again, let me rephrase it. 72 had heart disease compared to this ratio of the male, because the male are more. So if you do the comparison ratio and all, you notice that it was the female that had more, they are likely to have heart disease. So doing the positive coefficient of the target. So the slope is the peak exercise ST segment. This is a part of the feature in the data set. So I'm just going to explain it more. So according to the model, there's a positive correlation of 0.4, not as strong as sex and targets, but it is more than 0. So this positive correlation means that the model is picking up pattern that as slope increases, so does the target value. The slope is a feature in the data set. Let me just go back to data definition. Okay. Which is the slope is the slope of the peak exercise segments, this ST segment part of the data set. Yeah. Upsloping, flat sloping, down sloping. These are just medical terms and whatever. Can go back and research. So you know what I'm talking about. So basically what we've just done is we've gone through the analysis to analyze data, understand it better, get visuals, find the correlation, blah, blah, blah. Then we started use logistic regression, k-neighbors classifier, and random forest classifier. Our model logistic regression did better, but we fine-tune both model. But still after using random search CV and grid search CV for tuning the hyperparameters, logistic regression model performed better. So that we did our predictions and did our estimations. And now we've got our model. Then you can save this model and put it into production. So that's when you want to do DevOps part or the MLOps part. So that's that for our discussion for today. So if there are questions, let's go to the question the chat. Just drop it in the chat and I'll read it out. Okay, the first question here says, you mentioned cross validation during the hyperparameter tuning. What is the difference between the cross validation there and the one you just did? Okay, the difference is that in the random search CV and the grid search CV, it is the cross validation is already there in the function. So meaning it's even more better. What I also did with a cross validation score that was already provided by scikit-learn, it is more or less the same thing. So normally, like I explained before, let me go back to the meaning of cross validation score. Where is it? Where is it? Cross validation score is a function which trains the tests and tests the model over multiple folds of your data sets, different multiple folds. So this cross validation method gives you a better understanding of model performance over the whole data set instead of a single train test split score. Because if the normal one we did, we had a classification report, which is the score. So we did a cross validation score, splitting the data. Cross validation means you are splitting your data into different segments. You select the first one, and then you select the second one. So in the random search, the hyperparameter tuning, it also already has its cross validation also in the function. So they are basically the same thing. So meaning it's even more robust and better. So that's what it means. But now if you understand, just drop it in the chat. Okay. Can you please share the notebook when you're done? If it will be available, I'll let you know on Slack. If not, I'm not making any promises. Okay, what is the next question? Say, please, how do we know when to use a particular model? Like I said before, basically, in the previous class we had during regression problem, in the scikit-learn, since we are doing supervised learning, we are using scikit-learn libraries that has different estimators. There are classifiers and there are regression estimators. So the best way to know, just go to the documentations. There's a guide and a map for you to know, okay, this particular amount of data sets you have, this one might work better for this particular problem. So you just have to do your research on it to know which to use. Yeah, but sometimes I just try to choose the three best for my own research to say, okay, these three estimators are good, because basically random forest classifier is very solid. Then we have boosting method, SG boost, cat boost, and the rest. So just wait to do your own research so that you know which is better for a particular data set. Okay, then the next question, let me start sharing my screen. All right, for the next question, saying what I really don't get is how to select the S variable, which is the independent variable, when a data set might just have over 1,000 columns, which are independent. Is it that we have to combine all the independent columns to create X and the model will perform by selecting each column individually? No, the way you know your S, splitting your data into X and Y, the X part is all your data except the target column. Like for this, we have the target column, which is the column that has a yes or a no part. So you are predicting if a person has disease or not. That would be your target. So your X data would be all your features in your data set except the target column. So you drop that. Then for your Y variable, which is the Y data, will be just your target data, which is in this case our target column was if the person has disease or not. So it is not rocket science, it is part of the documentation. If you go to scikit-learn, you see the explanation there. It's not you guessing or the model guessing it for you. So do you understand? Have I answered your question? Drop it in the chat. So no. Okay, any other question? Drop it. Okay, thank you. You understand it now. Okay, another question From Gideon, after training the X, do we test it before testing the Y? No, you're not getting it. You're not training any X. What you're doing basically, yeah, using the train test split, you are getting your S train, your Y train, your S test, your Y test. You are fitting it to your S train data. Then you are scoring your Y data. So if I understand your question perfectly, you're saying after training the S, do we test it before testing the Y? Since you have to rephrase this question, because basically what you are doing from the scikit-learn library, the train test split, it will just split it for you. You are training the data, feeding a particular percentage of the data to the estimator, then a particular percentage will be for the testing. So I don't know if I've answered your question to how you asked it. Or you can also rephrase it so I explain better. If you understand, just drop in the chat so I know if you got it perfectly. Okay, understand? Lovely. Okay, any other question? We have time for like 3 or 2 more questions. Any other question? So basically, this is just a classification problem. It has a run through and a workflow of how you do it. So what we basically did was did the analysis, we got our model, we did classification metrics to understand the model better. Like I said, the way to understand classification metrics, that's classification reports, we have the accuracy. The default one for the classification estimator is the accuracy. So there's the precision, there's the F1 score, there's the recall score. So go back and do research to understand which would be better to use, because this we just use the accuracy. So for a different problem, you can decide to use the recall score. That's how you get to understand it better, to know, okay, this is what is I can use to see if my model is performing better or not. But sometimes you can have an accuracy score of 0.95. But for that problem, it's not accuracy that you need to use. You need to use recall or precision or F1 score. That is it. Okay, there's another question from my friend. Is the entire process for creating any model the same, or are there slight changes you can make according to your data set? Okay. There are some slight changes you can make to your data set, not the process of feeding your data to the estimator. That's when you call your EDA, your data analysis. You can clean your data, check the feature importance, remove missing data, drop some data that you think is not necessary, change the categorical data to numerical data. But after you've done all those, your analysis and whatever feature engineering and all, the process of modeling is basically the same. You split your data into X and Y. That is using the scikit-learn library for supervised machine learning problems. Supervised machine learning problem can have classification or regression problem. Unsupervised, that's when you have your clustering, rest, and deep learning, whatever. So, but after you've done your analysis, done your feature engineering on your data, then passing it using the scikit-learn method, that's the process workflow. You have to split your data into X and Y. Then you put it in a train test split, splitting into S train, Y train, X test, Y test. Then you fit the estimator to your S train and your Y train. Then you make your score to the S test or Y test. So that's just the process. And lots of, if you notice in this data set, they were not missing data, and they were all numerical data. So I didn't do feature engineering like using label encoder or using one hot encoder to change it back from categorical to numerical. Okay, I hope you understand my answer, Alfred. All right. There's another question from Abdulsamad. Is it compulsory to always use label encoder or one encoder on the target column if it is of the data object? That's an object data type. If it is compulsory to always use. Okay, basically, if your target column is not in numerical data, But basically, any data set, most data sets I've seen, the target columns are always numerical. But if not, if it isn't, the best thing I'll tell you to do is you have to understand your data set. First of all, you have to understand the problem you want to solve, basically. So, for example, if your target column, you want to see if this person has had this or not, it will be 1 or 0, or if the target column is saying yes or no, you can use label encoder. One hot encoder then would, why basically I don't like using one hot encoder is because it would increase the number of, it creates extra columns in your data. So the best I like using is the label encoder. Since it will see a part that is yes and a part that is no, it will encode it, give the value yes to 1, then the value no to 0 to no, 1 to yes. So you can use label encoder for your target variable. So, but basically, if it's a regression problem, you're trying to see the price of so car, or the price of this, or if the amount to buy this. So regression problem are always numbers, numerical. But in classification problem, your target variable like this, like we said, if it has this or not, it might have come in yes or no instead of 1 and 0. So you use label encoder for that. Because if you don't label encode it, and you pass it to the estimator, it will throw an error. Normally, anything that's passing through the estimator should be numerical data. If you pass it to throw an error. So I don't know if I've clarified that, just drop in the chat. If not, you can do more research on that. Okay, we have time for one more question. Okay, cool. Time for one more question. Any other question? Drop it in the chat. One more question. Just drop it in the chat. Okay, in the absence of no further question, I guess we'll have to call this a day. Hope you'll be able to get an understanding of this staging, because this is referring to the data science track. That's what they're doing in this course TC. So, and also other tracks are welcome to understand better. It will also help you in your premier projects. Okay, so thank you all for joining, and also for a quick reminder, premier project ends December 16th, and the deadline for submission of the projects, all your deliverables, the code, the GitHub links, the presentation slides, your documentations, and all deliverables, it's December 19th, and the presentation is December 21st. So this is just a brief reminder about that. And also your stage C, the current station ends December 20th. So you should know how to handle your timing with your premier project and your stage C course and deliverables. So do it on time to avoid hassles, and also submit your deliverables on time to avoid hassles. There are no extensions whatsoever. There is no form of extension at all. All right, thank you all for joining me. My name remains Angelo Christian. I'm the assistant program coordinator at Hamoy. See you next time. Bye.